So today we will start the interesting part in quantum computing because, well, so far we considered just one qubit. One qubit is fun, but you cannot do a lot of calculations if you have just one qubit. So we start today dealing with 2 qubits and with multiple qubits, and we will start considering the most interesting part of quantum physics, which is entanglement, which is the characteristic feature of quantum physics. Okay, first we start with some notation and mass background, because when we are talking about multiple qubits, well, there are many ways how we can denote the states, gates, and so on. So I will briefly go over that. I suppose well, a lot of notations are self-explanatory, so here are the different ways how we can write states of 2 qubits, 0 and 1. So there are many ways how we can do, but basically all of them are simplified versions, compactified versions of tensor product. So when we have 2 qubits, one qubit lives on its own phase space, which is Bloch sphere. Another lives on its own phase space. So the phase space for both of them is the tensor product. So how we can understand tensor product? If we take usual x coordinate, y coordinate, we take tensor product of them, we get a plane. So this is the same with qubits, just like the states here. Well, here like I have single qubit state, single qubit state. Okay, so this notation means qubit 0 in the state 0, qubit 1 in state 1. So we can form tensor product of many qubits as much as we want. So here I have qubit state 0, qubit state 1, and here qubit state plus. So I mix different bases. Sometimes it is very convenient to use such mixed notations, because if I would write the state plus in computational basis, I would get 2 terms. And now I can write just 1 term, so it's much more compact and understandable. One important note, like when we have such expression for qubit, where is the qubit 1, where is the qubit 2? So there are different ways how qubits can be numbered in such notations, and different sources use different types of numbering. So this is something to remember when you read papers or work with program, because it differs. So we will be numbering qubits from 0. So this is and starting from right to left. So this is qubit 0, this is qubit 1, qubit 2, qubit 3, and so on. So this is the way how Qiskit works, how IBM works, and yeah, like Qiskit and IBM. So everything, like when I will draw some formula here, you can use exactly the same formula in Qiskit and it will work. And in Qiskit, IBM, and Kirk, like qubit number 0 is at the top, so 0, 1, 2, 3, and so on. This is actually very inconvenient if you work with this, but it's good from point of view of like our using algorithm and so on. So why we use these notations? Because in these notations, if we say this is qubit 0, this is 1, this is 2, and so on, if we read this qubit state just as a binary number, well, we will get some integer. So with such notation, where you say, so this is 0, rightmost qubit is 0, so this is like the least significant digit in qubit, in binary base. This is the next significant, so on. I can simply read this state as a binary number. So this is very convenient for advanced algorithm. We will not be using any advanced algorithm, but this is the way how it is done. And when we add qubits in this program, we add qubits here at the bottom. So in analytical form, we will add qubits to the left. So these are qubits. But if we add several qubits, well, this number stays the same. So you don't need to change it. Okay, so this is something to remember. Now, what we can do with tensor product? So tensor product, you can consider tensor product the same as matrix product. So it's not commutative. Well, like with coordinate x and y coordinate, you cannot flip them, but it is associative. So you can perform all the operations the same as with matrices. For example, if you have qubit number 0 in state C and qubit number 1 in superposition state, you can open this parenthesis and write it as two terms like that. So using this way, we can write any state, say we can write this in computational basis. For example, if I have state 0 minus 1, so this minus is state like this, 0 minus 1 divided by square root of 2. If I want to rewrite this in computational basis, so here I replace the state minus with this explicit form, and here I have this parenthesis, I can open them and I have two terms. So this is quite simple. Okay, so writing this tensor product, well, is not very convenient, and therefore very often, like, you do not see this tensor product explicitly written very often. So we can omit it, write it like this. We can even compactify it further, just write it as a single cat. So 1, 0 means qubit 0 in state 0, qubit 1 in state 1. Okay, we can mix different notation styles when it's convenient, like, and when it does not lead to any ambiguity, of course. Say, for example, like if I have state minus and state I cannot write minus and I, because then it will not be clear whether it's like 2 qubits, one in state one in state minus, or just 1 qubit in state minus. There are some cases when we want to explicitly indicate like which qubit we are talking about. So in notation like that, we assume like this is the rightmost position, this is qubit 0, this is qubit 1, and so on. There are cases when we want to explicitly say, okay, this is qubit 0 and this is qubit 1. We can do it by adding subscripts like that. We can form subscripts like add subscripts for 2 qubits. So why, when this is convenient? So this is convenient in several cases. For example, I want to describe mathematically single qubit gate that acts, so gate Z, but gate Z that acts on qubit number 1. So gate Z by itself can be written in Dirac notation as 0, 0 minus 1, 1. Very simple. But to indicate that this is Z that acts only on qubit number 1, I add subscript. So this, now it's clear what this gate does. I can also, so this explicit notations also are convenient when we want to write some complicated multi-qubit states. For example, like this notation. Here I have 3 qubits. Qubit number 1 is in state 0, and qubit number 0 and 2 are in so-called Bell states that we will study in detail next lecture, 5+. So I can write it in very compact form like this. And now it's clear that this qubit in state 0, this is Bell state. I cannot write it simply 0, 5+, like without these indices, this would be qubit number 0, and this would be qubits number 1 and 2. Okay. Also, when we will describe measurement in multi-qubit system, it's very difficult, like if we don't use notation. Yes?
It's 2, 0 or is 20? So what is it?
It's 2, 0. Well, you may add commas, like if you have more than 10 qubits, but we will never use more than 10 qubits. So it's just qubit indices. Like. Okay. Now, mathematically, like when we are using this like this, mathematically cat vector for single qubit is represented as a column vector, like when you use some programs and so on. So, well, these computers do not use Dirac notations, they use matrix representation. So how to understand tensor product in matrix notation? So suppose I have this tensor product 0 and 1. So this is a column vector for state 0. This is column vector for state 1. So to calculate the tensor product, I simply move this right part inside, like this. So now I have 0 multiplied by this column vector, 1 multiplied by this column vector. So I multiply, so here I have 0, 0, 1, 0, and final step, just remove this inner parenthesis. And I have 1 column vector of dimension 4. This can be repeated when we have more than 2 qubits. For example, for 3 qubits, 0, and here 1, 0 that we calculated on the previous slide. So this is 1, 0 is column vector with dimension 4. Here I have column vector that corresponds to state 0, 1, 0. I move this rightmost column vector inside, multiply, remove bracket, and I get column vector of size 8. And you see how fast the size of column vector increases. So 1 qubit, we have 2 components, 2 qubits, we have 4, 3 qubits, we have 8. So in general, we have n qubits, we will have column vector with 2 to the power of n components. And it's very difficult to work by hand with such long vectors. Like it's possible to work with like vectors of size 4, so for 2 qubits. So this is what we can do. For anything more than 2 qubits, usually like Dirac notations are much better. They provide much more compact notations which are much more easily to understand and to do any calculations. Okay, but computers use this column vector representation because this is like linear algebra, and computers are very good with linear algebra. But even computers have very big problems with that. Say for 16 qubits, the size of this column vector would be 65,000 components. For modern computers, it's very easy. So you can do it on laptop like this Kirk, which is a web program on a web page. Well, it has maximum of 16 qubits, and it easily calculates like it without any special optimization or anything. So this is easy. But say you want to do calculations with 32 qubits, and that would be column vector of the size 4 billion. So the usual laptop like will run out of memory because it's 4 billion complex coefficients. So each 16 bytes, like if you are using double precision. So it's very difficult to do these calculations with qubits. If we have more than, say, 20, 30, 40, like for 40 you need supercomputer. There are, of course, different optimizations and different ways like how we can speed up this, but still like there are cases when we have to use like exact representation of this qubit. But that also demonstrates the power of quantum computing and power of this approach, like of using quantum states to do computations. Because with just a few qubits, 32 qubits, it's not a lot. So we have this state vector, which is huge, which can contain like the same information as RAM of a typical laptop. And it also means that to make practical computers, we don't need billions of qubits. Like if we would have like computer with just 1,000 of qubits, but these qubits would be perfect. You can do whatever you want with them. They live like for very long time, so you don't need to worry about noise. It's just 1,000 qubits. It will be quite practical, and it will solve problems that cannot be solved on classical computers. Okay. A little more about math, so about bra vectors and scalar products. So bra vector is adjoint or conjugate and transpose ket vector. We need them when we calculate scalar product, and we need scalar products when we calculate probability, when we calculate measurements outcomes, and so on. So calculation of adjoint is very simple, like we replace every ket vector with corresponding bra vector. What is important is that we do not change order of qubits. So in CAD vector, this is qubit 0, this is qubit 1. In bra vector, this is qubit 0, this is qubit 1. So it's very simple. You have CAD vector ABC and so on down to Z. Bra vector is the same, you just change direction of this angular brackets and that's all. So change CAD to bra and that's all. Of course, if you have some coefficient, you have to take complex conjugate of this coefficient. If we want to write bra vector as row vector, well, the same rules apply. So 1 here is row vector like this, 0 is row vector like that. You move right vector inside, multiply, remove out in parentheses, you get one vector of larger dimension. Now when we calculate scalar product, so this is important information because this is important operation because all measurements are evaluated through like results of measurements are evaluated using scalar products. If we have gates written in Dirac forms, and you calculate action of gates by scalar product. So scalar product for multiple qubit gates, well, it's calculated the same as scalar product for usual vectors. If we have several coordinates x, y, z, well, for one coordinate scalar product, it's just product of x and x coordinate. If we have several coordinates, we kind of add these results for different coordinates. So for qubits, scalar product splits into product of single qubit scalar product. For example, we want to find scalar product of 1, 0, state with state plus minus. So color code red corresponds to qubit number 1, blue color corresponds to qubit number 0. So I have such multi-qubit scalar product. It splits into products of single qubit scalar product. So here I have a product of 1 and plus, and 0 and minus. So this term describes everything related to qubit number 1. This describes everything related to qubit number 0. This scalar product is 1 over square root of 2. This 1 over square root of 2. Result is 1/2. Yes?
If you change the ordering of the qubits, what would happen?
If we have here 0, 1,
yeah,
that's a different state, because state 1, 0 means qubit 0 in state 0, qubit 1 in state 1. You switch order, you get 0, 1, that would be qubit 0 in state 1 and qubit 1 in state 0. So that's a different physical state. Then the scalar product may change in this case. Okay, if you want just to change order, like you want to write in different order, but you want to describe the same state. So here, like when we have explicit indication for qubits, we can flip this term. Because we know, like, so here I can write 0, 0, 1, 1. Because I have indices that explicitly specify about which qubit we are talking. If you don't use indices, then, well, position is important. So this is position 0, this is position 1, and so on. Here we have position indicated explicitly. Okay, so like, again, general rule, we have n qubits, we split scalar product into n terms. Difference with usual scalar product of vector where we add different components. So here we take product of them. Very simple. So sometimes we want to find partial scalar product. What is partial scalar product? I have here state of 2 qubits. And I want to find scalar product of this state of 2 qubits with this bra vector that describes only state of qubit number 1. When we want to do this, this is this is how we calculate outcome of measurement. So to calculate say outcome of measurement for single qubit state, we find scalar product of qubit and what states that we measure. If we have 2 qubits or more qubits, we can measure just a single qubit. How to calculate outcome of such measurement? We have to take such partial scalar product. We will consider this a little bit more detail later. So how to do this? Like, well, the rules are the same. So we have here a bra vector that describes qubit number 1. We pair it with ket vector that describes the same qubit. This is a scalar product, so this is just a number. This ket vector minus, well, it describes qubit 0. Well, and there is no corresponding bra vector. So the result of such partial scalar product is ket vector describing state of remaining qubits. Qubits with which we did not take scalar product. And again, it has physical relevance to measurement process. If we have 5 qubits, we measure 2 of them, for example, we know the states of these 2 qubits because we measured them. What about the remaining 3 qubits? Here they will stay, so this is how we can calculate them. And we will see this later. About single qubit gates. So suppose we have many qubits, we want to apply single qubit gates that we studied last lecture. How to do it? Easiest way is to denote to which qubit the gates apply. H0. This is Hadamard gate applied to qubit number 0. S1. Phase gate applied to qubit number 1. We can also use tensor product notations. A tensor product H. Again, rightmost describes what we do with qubit number 0. So we apply Hadamard gate to qubit number 0. We do nothing to qubit number 1. So here to write such thing, such operation with tensor notations, we really need this identity operator. Here, identity operator applied to qubit 0, so we don't do anything with it. We apply phase gate to qubit number 1. We can combine this tensor product using combination like this, or we can even write something more complicated, like this formula means, like multiplication of operators of gates has higher precedence than tensor product. But sometimes you can just put parentheses to be sure. So what this formula means? This formula means that we apply xt to qubit 0 and we apply hz to qubit k1, like that. Okay, so when we have many qubits, that's how tensor product of gates may look like. So this long formula simply means we apply Hadamard gate to qubit number 2, but we have 1, 2, 3, 4, 5, 6, 7 gates. Like it's not possible to understand it. So this is compact notations, usually it's better. We also can calculate this tensor product of gates as a matrix, again following the same rules for tensor product. This is the matrix for Z, this is the matrix for X, so we move rightmost matrix inside, we get a situation like this. We multiply these matrices by these numbers and remove inner parentheses, and we get matrix 4 by 4. Again, with 2 qubits, gates are described by matrices 4 by 4. This is something that we can understand. For more than 2, for 3 qubits, it's matrix 8 by 8. It's very difficult even to write everything. And so this approach can be used only for 2 qubits. Okay, so this is more or less everything about notations. So these notations appear in many papers, even in textbook, often without any explanation. Okay, now let's talk more about physics and so on. So when we are talking about qubit states, the most important thing, of course, what is the basis? When we have 1 qubit, the basis, like computational basis, is 2 states, 0 and 1. And general qubit state is a superposition of these two states, 0, 1. So when we have two qubits, like each qubit can be, like we can think, each qubit can be state 0 and 1, so pair of them can be in 4 states. 0, 0, 0, 1, 1, 0, 1, 1. So this is basis of two qubit state, computational basis, because we are using computational basis for each of them. So this is orthogonal basis, like in usual sense. So this is basis, so we can write any two qubit states as some linear superposition of the states. And it is orthogonal basis. So if we have like two qubit states written in this basis, we need to find scalar product between these two states. Well, we do not need to actually go into this like qubit by qubit splitting of scalar product. We can simply use these rules. That if we have scalar product of two different states, we have 0. If states are the same, we have 1. Orthogonal basis, very simple, very convenient to work. So, okay. So for example, let's consider this example. So here I have one state and I have another state. I want to calculate scalar product between them. So how do I do that? So here is the coefficient, so I calculate scalar product phi psi. So phi here stays as a bra vector, so I have to complex conjugate all coefficient of this. So coefficient near 0, 0 is I over 2. Complex conjugated is minus I over square root of 2. Corresponding coefficient here, 1 over square root of 3. Okay, so this is these two coefficients near state 0, 0. Then I have here state 1, 0, coefficient 1 over square root of 2. I complex conjugate it still stays 1 over square root of 2. Corresponding coefficient in state psi is 1 over square root of 3. Okay, there are no more coefficients here, so that's all. That's the answer. You simplify it, you get something like 1 minus I over square root of 6. So when we have two states written in this basis, in the computational basis, calculation of scalar product is very simple. Okay, so like this. So here is everything color coded. You get 1 minus square. What's important is to not forget to complex conjugate terms coefficient near bra vector. This is very common mistake. It leads to different results and you don't understand what's going on. Okay, so here in this basis, computational basis, this is like standard basis, we use the same basis for two qubits. So we write qubit number 0 in 0, 1 basis and the same for qubit number 1. We can use different bases. We can use bases, for example, for qubits number 0, I use X basis, state plus or minus. But for qubit number 1, I use 0 and 1. So these four states also form a basis. And this basis again, orthogonal basis. So if you have two states written in basis like this, and sometimes it is more convenient, you again can calculate all the scalar product and do all the stuff as with usual basis. Okay, so this basis we can call it ZZ, because for each qubit we write it in Z basis, so this is ZX basis. This qubit in Z basis written, this is written in X basis. And these are examples of product basis. So if you take any state here, so in this state, qubit number 0 is indefinite state 1, and qubit number 1 also indefinite states. And that goes for all these states, like here. Qubit number 0 in state plus, qubit number 1 in state 0. This is example of product basis. We will see next lecture that there are other bases that we can use. And you may wonder how that can be like if we have states, then of course qubit number 0 in some state and qubit number 1 also in some state, right? That's not necessary in quantum physics. Okay, now, so this is a standard computational basis, but this is basis. So general qubits basis, not all possible states. All possible states are written as superposition of these basis states. And we can write it as a column vector. So it's just, since column vector notations are often used for 2 qubit states, so coefficient I can write C00, C01, 10, 12. So this is how these coefficients are arranged in column vector. 00, 01, 10, 11. And if you know how to count in binary system, you see that this is binary 0, 1, 2, 3, and so on. So if you have more than 2 qubits, I want to write column vector, very easy rule to do it. Like, you don't need to actually perform all this multiplication, removal of inapparencies, and so on in computational basis. So here you have coefficient C with binary index 0, binary index 1, 2, 3, and so on. Very easy. And of course we have normalization condition, something to remember. Okay, now there is one important topic about multi-qubit system, and this is a measurement of multi-qubit system. Because measurement in multi-qubit system is much more interesting and actually powerful than measurement in single qubit system. When we have single qubit system, well, we can choose which basis we measure it, but that's all. We measure the qubit, wave function collapsed. State of the qubit after the measurement is the same as measurement outcome. So all quantumness disappears. We can do the same type of measurement for multi-qubit system. If I have 5 qubits, I measure 5 of them. It does matter whether I measure 5 of them all at the same time or I measure one after another and what. The result will always be the same. So this is an example of complete measurement. I have quantum system and I measure it such that there is like nothing like unknown remains. So I measure all 5 qubits. After the measurement, states of all qubits is defined by outcome of the measurement. So again, all quantumness disappears. I have complete wave function collapse for this type of measurement. But there are other type of measurements. So we can measure only a part of qubits, or we can measure some property of qubits. For example, if I have 2 qubits, I may not measure qubits directly. I may measure their parity, like whether if they are both 0 and 1, well, that means parity is even. If they 0, 1 or 1, 0, that means odd parity. I can measure parity. How exactly? Well, that's another question. We have to use the same tricks as with measurement in X and Y basis that you use or will use in your first lab. Okay, but we can measure this. So when we perform such partial measurement, there is still some quantum information that we do not determine through the measurement. For example, if I have 5 qubits, I measure 2 of them. So state of these 2 qubits collapses to the measurement outcome. But these 3 qubits, their state is not determined by the measurement. There is some freedom in this state. So there is only partial wave function collapse.
Yeah, but if I have 2 qubits which are in entangled state, if I have collapse of one of them, the second one also should collapse.
Yes, something, you are completely right. Something will happen to these 3 qubits as a result of measurement. So they will not be the same as before measurement. But the point is that which state they will be depends on how it is prepared. So suppose we have 5 qubits. I prepared them in some state. You measure them, and this is 0, 1, 1, 1, 0. This is what you get. This is the state of qubit after the measurement. So you know state of the whole system after the measurement. It doesn't matter how I prepared the state. It doesn't matter what the initial state was. But if I prepared state one way or another way, and you measure only 2 qubits, and you get 0 and 1, the state of remaining 3 qubits will depend on what was before. So, and that, of course, it may happen such that it will be completely determined, but that depends on how the states were prepared. So these partial measurements, they play a very important role in quantum physics and like in quantum thinking, or what we can do with quantum system. Because here, well, we have partial wave function collapse, but also this result of partial measurements, it provides us some information about what's going on with the other qubits that we have not measured. And these partial measurements are essential part of many quantum algorithm approaches. For example, quantum error correction is based on that. Quantum teleportation, quantum distillation. There is the whole approach to quantum computing, which is called measurement-based quantum computation or one-way quantum computation. So that's very different than what we consider here. There are no gates. So initially, there is some prepared, very complicated states of many qubits. After the state is prepared, what we do, we just measure qubit after qubit. Just the measurement. But which qubit we measure and in which basis, it depends on results of previous measurements. So and using just this approach, we can realize any quantum algorithm. So using just partial measurements, one after another, conditional, so what we will measure next depends on previous results of previous measurement, but this is very powerful tool. Okay, so just to give like brief example, quantum error correction, how it works. How classical error correction works. Suppose we have some bits which are not very long-lived, like there are some errors. And I want to keep information safe. So what I can do, I can keep 3 copies of a bit. So instead of 0, I will write 0 in 3 physical memory cells. So one logical 0 will be represented as physical 0, 0, 1. And 1 is 1, 1, 1. If there is some error, so one bit flips like this. Like you just look at this form and you say, okay, here this bit flipped. We can read it. If we see a situation like that, we change it to 0. Okay, we have perfect state. We can do the same with quantum stuff. So for example, like if I want to encode logical qubit state like this, I can encode it into 3 qubits. I have the same coefficient C0 and C1, but here instead of like 1 qubit carrying this 0, I have 3 qubits, 0, 0, 0, 1, 1, 1. And suppose error occurs. This qubit flips. Well, when you look at this state, you can say, okay, this qubit flipped. And you can correct it. You can simply apply X gate and correct it. X gate flips 0 and 1. But how to do it like in quantum computer? We cannot read qubits. Because if you read qubit, say you read this qubit, you will get either this term or that term. Superposition will vanish because there will be collapse of function. So how do we do this quantum error correction? We do it by parity check measurement. So we can measure, do not measure qubits directly. What we measure only parity of these qubits. For example, I take parity of this qubit. So here I have 2 qubits the same and 2 qubits the same. So parity is even. What is important, this term is even in parity, and this term is even in parity. So if I get like even parity, like I do not destroy this superposition, because both of these terms in superposition corresponds to the same measurement outcome. So superposition is not destroyed. And I see that, okay, so here I have even parity. That means that these two qubits are the same. That means they are correct. Because they are same, and like we assume as always that probability of double flip is very low. So if they are the same, so that means they are correct. Then I check parity of qubit Q0 and Q1, and I see that this parity is odd. Again, it is odd here, and it is odd here. So superposition is not destroyed. I keep this state intact. But I see that parity is odd. Okay, so one of these two qubits is wrong, is flipped. I know that Q0 is not flipped. So I can deduce that Q2 is flipped. I apply X2 gate, and I correct the error. So this is how error correction works. It is very important to use partial measurement. So we can use partial measurement of quantum system to get information about this system, such that, like, and if our measurements are properly designed, we will not destroy superposition. But we will get some information that allows us to do something with this state, like correct errors or teleport qubit. Yes?
And if I check parity of one state which I don't know and another one is already collapsed, then it means I principally the same as reading the unknown state. So
suppose we have two qubits in some like states that doesn't have particular parity. Something that says combination of all 0, 0, 0, 1, 1, 0, 1, 1. So some general states are somehow prepared. You measure parity measurement. You do parity measurement. This is what will happen. You have state C0, 0, 0, 0 initial, general state. You perform parity check on these two qubits. Now these two terms, they correspond to even parity. These two terms correspond to odd parity. So outcome of this parity check measurement will be random, either even and odd. The same as when we measure qubit, well, we get like random result, like if this qubit is not particular. If the outcome is even, what we will have partial collapse. We will not have all the terms. We will have only even terms. If the outcome is odd, we will keep these terms. So here, in such case, there will be partial collapse of wave function, and this wave function will like there is randomness, so we have wave function collapse, and we have two ways possible: even route or odd route, like that. With example, with parity check measurement, I show the situation when qubit flipped. But in reality, so we will have, like this flip of qubit is also probabilistic process. So what happens in reality, like in such error correction, we will have a combination of flip terms. We will have combination of these flip terms. And original and flip terms. So wave function in this case will be this plus that with some weights. And then, like if we have the combination of these four terms, we perform parity check measurements of these two qubits, and here they are all even, all 4 terms. So wave function doesn't collapse at this point. And then we perform measurement of parity of these 2 qubits. And here this parity is even when we don't have error. And here it is odd. So at this moment we get split into 2 possibilities. We cannot choose which possibility we will choose. They depend only on relative weights. We may get this route, and we will see that, okay, here this parity is even, so everything fine, we don't need to do anything. Or we can choose this route, and we will see here parity is odd. But parity is odd, we can apply X gate after the measurement to flip this qubit and go back there. Yes?
Yes, sorry for asking, it's very tricky. But if there is no error happened, yes, we have this first state, and you measure, you always will have parity even. And if you have result parity even, it means that you already collapsed for this parity even.
Yes, that means that we collapse into this state. What's important? Both this term has all parities even, and this term has all parities even. So there won't be collapse that we will go only into this state. Say, if you measure just 1 qubit directly, you will choose either this term or this term. Superposition is destroyed. We lose quantum information. But using parity measurement, we keep this term together. And if there is error, result of measurement tells us what type of error we have, and we can correct it. Okay, so this is really important to understand this partial measurements. So, but first we will consider like very briefly complete measurements. They're simple. When in complete measurements we measure all the qubits. Wave function collapses, state of the qubits is the same as outcome of measurement. For example, what happens if we measure such state in computational basis? So what will be the outcome of the measurements? Well, in this case it is very easy to calculate without any mathematics, because probability that we will get state 0, 0 is just this coefficient squared. We can find these probabilities using general rules that probability of outcome is scalar product of this outcome with wave function, everything squared. So, but if we have it written in such form, it's very easy. You just take this coefficient, absolute value squared, this is your probability. This formula is useful when we have some more complicated measurements. For example, measurements in like computational basis are very easy. You don't need to use this formula in reality. But what if you want to measure qubits in a different basis? For example, what if you want to measure these 2 qubits in basis ++? You can take this state and rewrite whole state in X basis through plus and minus ket vectors, but this is usually very long procedure. If you want to know, say, just the probability that you measure in X basis and 2 qubits will end up in state plus, you take scalar product of this state, this plus modulo square. So this is very useful formula if we have something more complicated than just measurement in computational basis. And this is very general formula. This is Born rule. It applies to like basically every possible type of measurements. Okay. Now we will go into more general measurements that include projection measurement and complete measurement. That include partial measurement and complete measurement. So this is called projection measurements. Because what we do when we measure quantum system, we project this quantum system into some states that we recognize like as classical outcomes. For example, when we measure qubit in Z basis, we classically recognize state 0 and state 1. So we project, like we have qubit here on a Bloch sphere somewhere here, and we force this qubit to go into one or two states. So we project this qubit state into such basis. So any type of measurements we can do, well, it's all some kind of projection measurement. There are some physical, like say classical states that we can recognize that lead to different measurement outcomes, and we project the state of the system to fall into one class or another. The same as I showed with the example with this error correction. If we have both correct terms and incorrect terms, we measure parity and we project it. So it falls either into even parity class or odd parity class. When we measure parity, we cannot get, okay, there is superposition on odd and even. We force wave function to choose. Please choose, are you odd or are you even? And go into one of these two possibilities. So this is projection measurement. So how to describe them in general? So let's look at this formula. So this is a formula for probability of outcomes 0, 0. So this is absolute value of this scalar product squared. I can rewrite this absolute value squared as follows. So first of all, this is absolute value squared, so this is this quantity times conjugated quantity. Now I can use properties of scalar product. In scalar product I can flip this psi and 0, 0, so I can rewrite this 0, 0 of psi as psi 0, 0, but well, I need to conjugate it once again. So if you flip two terms in scalar product, this is the same as conjugation. And then when I write it in such form, what I have inside is such cat-bra combination. And cat-bra combination in quantum physics is some operator. So here I have some operator, M00, and this is such operator. And what is this operator? This is projection operator. So it takes 0, 0 component of whatever state it acts on and just keeps it. So this is the same as classically you would write operators, say XX, unit vector X, unit vector X. That means like you take only X component of vector to which this operator applies, and you keep just this direction. So this is projection operator. It takes only 0, 0 component of state and it leaves it at 0, 0. Any operator can be written through certain, any measurement can be written through some projection operators. Okay, and we can obtain similar expressions for all other outcome of measurements. For example, what is the, if we want to measure say 0, 1, a probability of 0, 1 state. So here this operator will be 0, 1 and 0, 1. Take only 0, 1 component of wave function and keep it. Drop everything else. This is exactly action of projection. You have a vector and you say take only x and y component of this vector and drop z component. This is projection. Or take only z component of this vector and drop x and y. So you project it on z axis. So this is projection operator. And probability of our outcome, like this is the formula for expectation value. So I have operator inside to this psi sandwich. This is expectation value. Okay. So probability of any measurement, or probability of outcome, of particular outcome of any measurement can be written as expectation value of a certain projection operator. And this is the basis for all type of measurements that we can imagine. So we can, if you can imagine some measurement, then that means that you can write such projection operator for each outcome of the measurement. And whatever can be written in such form can be measured. Whatever cannot be written in such form cannot be measured. Okay. Yeah. And such measurements, well, they are called projection measurements. So there are several mathematical properties of this operator. So first of all, it is projection operator in mathematical sense. Like if you take m squared, you form 0, 0, 0, 0, and then you put it again. So inside you will have scalar product 0, 0, and 0, 0, which is 1. So m squared is m. So this is mathematical property that define projection operator. What does it mean? That applying this operator twice is the same as applying it once. So you take z component of a vector, you get vector along z. You take z component again of this vector, nothing changes. You already projected it. Physically, this means that the system will be like the state of the qubit that we measure will be the same as measurement outcome. So if you measure the same thing second time, you will get the same result. This operator must be Hermitian. Why they must be Hermitian? Well, so for Hermitian operators, expectation value is real and probabilities must be real. Okay. So when we perform measurements, we get several possible outcomes, at least two, because if it's only one possible outcome, it's not measurement at all. So there are at least two, but there can be more. For example, in complete measurements of 2 qubits, we have 4 possible outcomes. So each outcome of this measurement is described by its own projection operator. And this set of operators also can satisfy some collective properties. So these are the conditions, the projector plus Hermitian, these are conditions for each operator. But also this set satisfies two conditions which are, again, physically clear. So product of two operators must be 0. What that means? That these measurement outcomes are mutually exclusive. So we cannot get outcome 1 and outcome 2 at the same time. No. So if 2 qubits are even, they are not odd. Like if the state of 2 qubits even, it's not odd. That means also that we cannot perform measurements like we cannot distinguish between state 0 and state plus, because measurement operators for these two types of outcomes, they are not mutually exclusive. We cannot measure it. So this is like mathematical formula for indistinguishability of non-orthogonal state. And the last condition is the set of this projection measurement. If we add them, we should get identity operators. What does it mean? Is that this set of measurement outcomes is complete. So like here, if we perform all measurements of complete measurement of 2 qubits, we have to consider 4 outcomes. I cannot like write only 3 outcomes because, well, there is possibility that system is in this state. So this is this mathematics. Okay, so when we have, so when we describe arbitrary measurements, we basically have to describe like this projection operator. This is, sometimes there are shortcuts and we can do it simpler, but in most general case, if we want to perform some complicated, very fine-tuned measurements, well, this is the way to do. We define this set of operators, we check that they satisfy these properties, then we will also have to think how to realize it in quantum computer or whatever quantum system we have. But mathematically, this is like the step. You define the step, then probability of each outcome is just the expectation value. And what is the state after the measurement? State after the measurement is basically, this is this projected state. So this is your initial state in which you apply measurement. This is this projection. So this is projected state, but we have to normalize it to 1. So normalize, because the length of this vector is like, well, this is the length of the vector. is probability. So we have to normalize. So in projection measurement, we say like, okay, we have state like this, we project it, say, to the axis, and then we have it scaled down, scale up, so its length will be equal to 1. So, and everything is described through this projection measurement. Okay, so this is like the summary. Now, how to do these calculations, like when you need to do it? So formulate measurement operators, projection operators. Sometimes it's very simple, sometimes you need to think about how to define, but usually it's not very difficult. Then you want to find outcome of measurement. So you have quantum system in a certain state, you find unnormalized collapse state. So you apply this operator to this, to the initial state. You do this for each measurement outcome, only for outcomes which are interesting to you. Probability of this particular outcome is the length of this unnormalized function. And then finally you normalize it and you get your final state. And this is absolutely general measurements, general approach which you can use for absolutely any type of measurements. Okay, let's. Yeah.
A few questions.
Okay.
So projection, it's easy to understand this one qubit, yes? It's like the geometrical projection. Is it the same that we can have a positive and negative outcome after we do projection?
Well, it's like there are more than often there are more than 2 outcomes. For example, like complete measurement of 2-qubit system. We have 4 outcomes: 0, 0, 0, 1, 1, 0, 1, 1. So, but this all directions, they are also like orthogonal direction in this phase space of 2 qubits. Well, it's when we are talking about more than 1 qubit, it's already very difficult to have some geometric representation. Because for 2 qubits, for 1 qubit, we have Bloch sphere. Beautiful. Everything can be understood with that. To understand 2 qubits, you have to take 1 Bloch sphere, then take second, and make tensor product of that. You will have 4-dimensional construction, which is difficult to imagine. So here we have to, so we can think about single qubit analogy, but we have to rely more and more on math. Or when you do this calculation, sometimes you can't understand it.
And about collapsing, so if we do apply this operator of projection to qubit system, so we do not collapse it, but we also lose kind of information about qubit, yeah? So if it's 1 qubit, there are many states, if you'll give me the same projection.
Well, if there are many states, well, we project like only to state 0 or state 1. Okay, if when you talk about many states that has the same probability, not the same projection, but the same probability, these are all superposition states. So because to have the states which are, so this is 0 state, this is 1 state. Any state at an angle is a superposition of 0, 1, 1. You measure, you project it, you force this wave function to align with the axis, either like this or like that. And you are losing superposition. So every time there is collapse, there is some loss of information about this.
But before I measured, I didn't lose it yet.
Yes, like you have qubit like that. Well, you have some information that exists in this superposition of 2 coefficients, but you measure it, you choose 1 or second outcome, and you are losing information. Okay, so let's consider briefly one example, measurement of a single qubit. So this is the state. Suppose I want to measure qubit Q0, just this qubit. Just qubit Q0. How to do it and how to describe post-measurement state of the system. So if I measure qubit 0, so this is the projection operator. So what are two possible outcomes? Well, I measure one qubit, so I can get 0 or 1. This is projection operator for outcome 0. This is projection operator for outcome 1. So here, this 0 and here 1 is the outcome. I need to use subscripts to indicate that I measure only qubit 0. So here I have to use this subscript. Okay, and then I need to apply this operator to the state. So I apply this operator to the state, and to calculate this, this application, you see, when I put this operator here, well, I will have partial scalar product. I will scalar product of this 0 state of qubit 0 with this 0, 0. This is a partial scalar product, so this is why we need partial scalar products. Okay, when we apply this state, when we apply this operator, actually in this case it's quite simple. This projection operator will select this term, and it will select this term. So it selects term in which 0th qubit is in state 0. So in the outcome of this, so in post measurement state, if I get outcome 0, post measurement state will have 0, 0 and 1, 0 with coefficients that has ratio like this. This measurement outcome will select these two states. So when you do the math, so this is what you get. So I just do this math at home, so it's not very difficult. So when you calculate this application, when you apply this this operator to the state, you get state which is not normalized. To get probability of outcome, you have to find its norm. So this is the probability of outcome as a norm of the state. And then you normalize the state to get normal state state vector with length 1. So so this is a post measurement state for two different outcomes. If outcome 0, well, qubit 0 is in this state 0. So I measured only this qubit. So after the measurement, I know its state. But state of the other qubit may be different. And what is important here, that when we compare these two states, you see that they are different. So post-measurement state of qubit, so I have two qubits. I measured one qubit. I didn't do anything to the other qubit. But depending on outcome of the measurement, state of this qubit is different. And when we are talking about two qubits inside a quantum computer, that's kind of fine. But we can talk about photons. We can prepare this initial state, this state, with two photons. And we can send one photon to the other side of Earth, or to the other side of solar system, and measure first photon only after that. So according to the theory, at the very instant we measure photon here, photon on the other side of solar system switches its state this or that. Spooky action at a distance. And this is the signature of entanglement. So this is like the main feature of quantum physics, something that we will be dealing from now on. Basically, we'll be talking about different aspects of entanglement. Okay. So this is something that, well, many people, including Einstein, well, were not happy about, but this is a very important and feature of quantum physics. And like next week on public lecture during our seminar, I will try to show it in real time that it's real. Never tried it in real time, but well. Okay, so What is quantum entanglement? It's a form of quantum correlation. Quantum correlation between quantum particles, qubits, photons, magnons, whatever. It is a form of correlation in which two or more particles, they have well-defined state of a system. So I have two qubits, I can write wave function for two qubits. But states of individual particles are not well-defined. So let's consider one example. So suppose I have such state of two qubits. I want to find states of individual qubits Q0 and Q1. So I want to write this state and add product of this qubit state. So this is state of two qubits. So I want to find what is the state of qubit number 1, what is the state of qubit number 0 and qubit number 1. So we can write this state as a superposition, general superposition. And then I can calculate this tensor product using just general rules for calculating tensor product. So I will have 4 terms that corresponds to 0, 0. So here I have this product of coefficient alpha 0 and alpha 1. This is 0, 1 term. So here I take this 0 from qubit number 1 and 1 from qubit number 0 and so on. So this is the state of two qubits, and depending on these variables alpha and beta, I may have many different representations, many different states written in computational basis. And this state I want it to be equal to my state of two qubits. So these terms must be equal, this term must be equal, and so on. So I obtained 4 equations for each of these basis components. So we obtain 4 equations, and plus we have normalization conditions. So we can solve this system of equations. For example, I may try to express all these coefficients through alpha 0. So this is like I have first equation, and from this equation I can write alpha 1. Well, I solve it. Alpha 1 is 1 over 2 alpha 0. Second equation allows me to write beta 1 is a function of alpha 0. Third equation, well, in third equation I have alpha 1, which I already know. So I can find like third coefficient. And this is the last remaining equation. In this equation I have beta 1 and beta 0. I already know them. So I can simply substitute these calculated quantities, and I see that indeed when I multiply them I get minus I over 2. The same as I have in the state. So this fourth equation is satisfied automatically. Okay, and here I find everything, and I express this through coefficient alpha 0. I don't know this alpha 0 coefficient, so how to find it? Well, we have normalization condition. State of this qubit must be normalized. So I can find, I can use this normalization condition, and I can find alpha, which is like arbitrary phase factor divided by square root of 2. So the system is solved. I know alpha 0, I know alpha 1, beta 1, and beta 0. I know all 4 coefficients in this state of qubit 0 and 1. So this is the state of two qubits, and I can write it as a tensor product of one qubit state and second qubit state. This is the state of qubit 0. This is the state of qubit 1. When we look at this state, it's not immediately clear that we can do this. But solving this equation, it's quite easy. So what we have here? We have here this undefined factor gamma. But it is just a global phase for qubits. So, and I can assign some global phase to one qubit and opposite global phase to other qubit. Well, anyway, this global phase, it doesn't matter. So everything is solved. Okay, so here I wrote this 2 qubit state as a tensor product of single qubit states. So such states are called product states, Because they can be written as a product, or simply separated states. And these states are more or less similar to the states that we encounter in everyday life. Because here I have qubit Q0 in a certain state, qubit Q1 in a certain state. So Q0 is some point on a Bloch sphere, Q1 is some point on a Bloch sphere. So I have just a collection of qubits that, well, behave as a usual collection of classical particles. Consider another example. So it's very similar state, but this time I made small change. Here I changed sign from minus I to plus I. Everything else stays the same. Okay, and I also want to find like what would be individual qubit states for such wave function. Well, we proceed as usual. We write the superposition for this fourth system of equation. In this fourth system of equations, the only difference will be signed here in the last equation. Then I solve equation one by one. I solve first, second, third equation. Results are exactly the same. And I come down to the last equation. You see, the previous equations are the same. So this product B1 and B0 is the same as it was before, minus I over 2. But in my state here is sign plus. So this is what I got from previous equation, and this is what I need to have. And so this system of equation cannot be satisfied. It does not have solutions. So this state in such form with just one sign flipped. This state cannot be written as a product of single qubit states. So for such state, like if you ask a question, what is the state of qubit 0 here? I don't know. It's not defined. We cannot define it. What is the state of qubit 1? Well, I don't know. At the same time, I have perfectly fine wave function for 2 qubits. So I have state of 2 qubits which is well defined, completely defined. But in this state, states of each individual qubits are not defined. So this is entangled state. And this is what it means, is it's like 2 qubits or 2 particles or 2 quantum systems, they form inseparable state. I can completely describe state of the system, but I cannot describe state of individual parts of the system. This is the signature of entanglement. Okay, so entanglement is the most important quantum property, like absolutely most important. It's the characteristic feature of quantum physics. Like real physics starts not with the wave mechanics, because we have waves, classical waves. So the fact that electrons have wave properties, okay, well, we know that waves exist. And we know that light has wave properties also. Often it's seen like rays of particles. So this is not like real quantum physics. Real quantum physics starts when we have entanglement. So an entanglement there are many like interesting properties of entanglement. So one property is like states of individual qubits are not defined. As a consequence of this, we have this phenomenon. So when we measure one qubit and do nothing to the second qubit in the entangled state, then state of the of this second qubit changes depending on the outcome of measurement. Okay. So this is a signature of entanglement. If 2 qubits are not entangled, like if we have particular state of one qubit and particular state of another qubit, we measure this qubit, nothing happens to that one. So this dependence of post-measurement state on outcome of the measurement is a signature of entanglement. It may seem that like we may use this for some like instant information communication, we can send information, because like we measure state of photon here and state of photon on the other side of galaxy instantly changes. But we cannot use this effect by itself for transfer information. Why? Because we cannot choose between these two outcomes. When we perform measurements, we get random results, here or there. We cannot choose which outcome we will get. We get it random, and therefore, well, we know at the very moment we perform measurement, we know what will be the outcome of measurement at the other side of galaxy. Yes, that we can predict, but we cannot use it to transfer information. So entanglement requires interaction. So if we have two particles that never interacted, well, they will not be entangled. So we cannot produce entanglement using single qubit gates. So when we're talking about qubits, we have single qubit gates. No matter what you do with these single qubit gates, well, you will qubits will remain not entangled. And the opposite is also correct. If we have entangled qubits, two qubits entangled, you apply single qubit gates to each of them. Qubits remain entangled. So single qubit gates cannot create or destroy entanglement. Entanglement can be destroyed by measurement. We have two entangled qubits. We measure one of them. Of course, entanglement is destroyed because after the measurement state of this qubit will be definite. Okay, so this interaction, it can be either the direct interaction between qubits, or it can be interaction mediated by some like third qubit or something else. And speaking about magnonics, it would be very interesting to use magnons to entangle large number of qubits. So if we can send some spin wave or some magnonic state and entangle hundreds of qubits, it will be very useful. Entanglement is non-local, as I already said, so if we have two photons, well, move them at very large distance, they remain entangled. This non-locality was checked with photons. It's also very interesting to check whether this non-locality remains with magnons. If we have propagating magnons, we create entangled state of two magnons and then propagate at long distance in solid state. So are there any limits to entanglement, to distance or to time of entanglement, which is related to interaction with solid states? This is one of the questions for which quantum magnonics may be very useful for fundamental physics. Okay, entanglement in modern quantum computation science is a resource. So what is done in many quantum algorithms is that we create entangled state of two qubits, and this entangled state does not carry any information by itself. So it's not like entangled states encode 0 or 1 or something. It's just the entangled states is that, well, we have this state. And then we can use this state to achieve some effects. And here in this course we'll consider how to do it to achieve quantum teleportation. Or maybe also super dense quantum. So we first create it, and we have this entangled pairs of qubits or triples of qubits, and we keep them and we use them when we need it. So this is resource, and this is very valuable resource in probably the most important resource in quantum physics. Okay, and finally, the last few minutes, let's consider some examples of entangled states. So first of all, there are much more entangled states than product state. If you write random, like you write 2-qubit state, for example, use some coefficient C0, 0, 0, 1, 1, 0, 1, 1, choose random values of this coefficient. This state almost certainly, like if you choose random values, this state will be entangled, as mathematicians say, with probability 1. So you need to fine-tune this coefficient to get non-entangled state. So in reality, they are much more common than product state. Okay, and states, so there are different levels of entanglements. They can be entangled weakly or strongly, and we will not go into exact mathematical definition, but for example, like in this example, we measure one qubit, we get two different orthogonal outcomes of measurement, of course. And here states are, we have different states. So we can characterize how different these states are simply by taking scalar product between them. So if states are the same, scalar product is 1, and that means we have product state. If states are orthogonal, these states are orthogonal to each other. States of the other qubits that we don't measure, if the states are orthogonal, this is like the most different states. If the states are close, well, then scalar product will be between 0 and 1, or absolute value of scalar product, of course. So there are different levels of entanglement. And there's several important maximally entangled states. So one state is a Bell state or Bell pair. So this is like the most important state in quantum physics. It's used like everywhere. And we will consider this state next lecture. We'll devote the whole lecture to properties of this state. Another state is so-called Greenberger-Horn-Zeilinger state, GHZ, and yes?
So there can be partially entangled states.
Yes, yes. So well, it's not partially like it's entangled state, but not maximally entangled state. So they call just entangled. Partially entangled state is a term which is usually used for system of more than 3 qubits. For example, I can have 3 qubits, and I can have 2 qubits entangled and 1 not. That's partially entangled state of 3 qubits. This is state of 3 qubits, and this is example of completely entangled state. I have 3 qubits, and each of and there are entanglement between all 3 of them. We are talking about levels of entanglement. We are talking about maximal entanglement, not maximal entanglement. Well, you can introduce different measures, like put number to it. But the idea is like that. Okay, so this is GHZ state, or as Andrei would probably call, because he is also working in microwave, comes from microwave physics, gigahertz state. Yes, so some gigahertz states, but GHZ state, so state like that. Okay, and it can be it's important state in you can do some interest in like quantum sensing, like important state for quantum sensing, as like you can achieve very high sensitivity of quantum measurements if you create like generalization of the state with many qubits, like combination of all zeros and all ones. Okay, so this is one of this such characteristic state. Another example is W state. It's a state with 3 qubits, entangled state, and this state you cannot transform it into GHZ state. Like using any local transformation, you cannot move from here to there. So these are like different classes of entanglement. What is interesting about this state is that this state is very robust against losses of qubit. Like if you consider this state, if 1 qubit is lost, well, entanglement between other 2 will also be lost. So it's like all or nothing system. Here in this state, if 1 qubit is lost, like somehow interacts with environment or something like that, the remaining 2 qubits will be entangled. Again, we can write of generalization for n qubits, so there will be n term. And this is the state like in which we have n terms and only 1 qubit is flipped in each term. So this is essentially magnon state. Very interesting question is like maybe long life of magnons, like in solid state, is related to this robustness against entanglement. The W state, like it's known that it's robust. We are losing one qubit of the state, this state remains entangled. The same will be here. So we are losing 1 spin in magnon, but we still have magnon. And it would be very interesting to do some kind of experiments to check this, whether there is relation between lifetime of magnon and robustness of W states, of entanglement in W states with respect to qubit laws. Okay, so that will be all for today. Thank you for your attention. Any questions? Okay, there were a lot during the lecture. Okay.